All right, good morning, everyone. Welcome to if you're in Cambridge, a snowy morning. If you're outside of Cambridge, maybe you got even more snow. I was kind of disappointed we only got 3 inches here. But anyway, so we'll go ahead and get started with a soft start as usual, talking about an application of regression. And then we'll go into the main material for today. So the paper that I want to talk about for this soft start is one called Mating System and Brain Size in Bats. Hit Nick.
I think Finale froze again. She's been having technical problems. Are you still there, Finale? She froze. So while we're waiting for her to reboot and come back, I know Finale has a favorite example she's going to share in regards to regression and bats. And I'll let her get back to that. My example that I wanted to share is in regard to the use of regression models for earthquake modeling. Not sure how many of you have seen this type of work, but obviously one problem with earthquakes is to try to predict the aftershocks. And so you can imagine training a regression model where you feed the model the location of the main shock and the location of aftershocks. And the model is trying to predict the spatial distribution of where you'll find aftershocks in that environment. Right, so this is work by people like Brendan Mead, who some of you may have taken a gen ed class with him, where I think he talks about some of these. He's a professor in EPS, and he's actually using neural networks to try to build these predictive models, in this case, of earthquakes. I think it's a nice example of here the regression target is the location of the aftershock. And it's a nice example of new ways in which we're using machine learning to actually better understand, in this case, the physical world. And one of the things that they do with their model is not only do they show that it's much more predictively accurate of the location of aftershocks than, say, the typical rules that physicists would have used in the past, but they're able to actually go inside the neural network model and interpret the model and ask questions about what are the physical properties of the world that it's picking up. So not only do you end up with a ability to be more effective in predicting the location of aftershocks, but you end up in that case with new physical understanding as well. One other example that I will give you while we're waiting for Finale to come back is, so there's a lot of use, again, in the physical sciences at the moment of trying to predict the physical properties or the chemical properties of materials. One of the challenges we have at the moment is energy efficiency. And it's interesting to try to find molecules that can be more efficient in harvesting energy from the sun. So the regression problem there is to try to predict the efficacy of the molecules in regards to their ability to convert solar energy into electrical energy. This is work actually, again, that was done by collaboration between computer scientists and chemists at Harvard that ended up identifying molecules that were much more effective than anything we knew at that point in time in terms of harvesting energy, and were actually licensed by a big chemical company and have played a role in the revolution we've seen recently in terms of new solar energy technologies. So last Thursday, I think we gave you examples from commerce, and those are a couple of examples from science to help you to see some of the other places where regression models are playing a role. And yeah, I see Blake, the chat. Yeah, Alan answered it in chat. So kind of neat applications of where we can use these type of things. Also, somebody like, again, I'll chat his name while we wait for Finale to come back. Somebody like Matthew Schwartz, some of you may have interacted with. He's a physicist at Harvard who's using machine learning to do high energy physics in a completely new way, trying to understand, I mean, it's kind of the type of high energy physics that I don't understand very well, but physicists deal with very high dimensional data, and they're trying to understand patterns in that data and trying to predict properties of new particles. And Matthew Schwartz is an example of a scientist here who's using deep learning, in his case, in all kinds of new ways. While we're waiting for Finale, let me maybe situate what it is we're going to be talking about this morning. Last week on Thursday, I gave you a first look at classification. And that first look at classification was through very simple linear models.
Hey, David, I'm back. Sorry, can you hear me? Okay. I apparently, yeah, sorry guys, it crashed and then I came back and no one could hear me. It's like, okay.
Okay, great. So I gave them some
about an example
of regression. I think we can probably dive into the probabilistic viewpoint.
Yeah, no, that sounds great. We'll save bats for another day.
Welcome back.
Cool. Hopefully this time it stays that way. But yeah, so before I get started with the main technical material, let me just mention a couple of notes in terms of things coming up for class. So first note to emphasize is that the homework, first homework is due this Thursday at 8 p.m. And for that homework, if you would like to use some, you have late days available. So we have it due on a Thursday. So if you want to take your wellness day to be truly a wellness day, a day off, you may. But if you want to continue into it, you know, the late days are there. You don't have to ask for permission to use the late days. The whole point of the late days are that they're just available to you for any reason, no questions asked. The other thing that I want to mention about the homework is that there's been several clarifications, but one important one is on question 4. So there's a new file, question 4 Python file in the GitHub repo. If you pull from the repo, you can get that updated file. If you pull, make sure, be very careful not to overwrite your own stuff. If you just look into the file, the new file as well, you'll be able to see where we have made changes. And the key change there, I think, is actually kind of useful for us to kind of bring out, as you know, it's a bug that was in the problem set, but an interesting or useful bug for us to think about. And so the bug that was coming up is that your x-axis for your problems in question 1 were years, right? So like 1960, 1965, etc. And these are fairly large numbers. So when you use a polynomial basis and you raise that to the 5th power, you got some numbers that were really large. And when you multiplied those together, to form various correlation matrices, you were suddenly getting numbers that were even larger. And this was creating some very ill-conditioned matrices. So things that, theoretically were invertible and should have been totally fine were in fact not totally fine at all, right? And so the change that we have made in the code for that problem is that instead of dealing with years as being from like numbers like 1,960, we're subtracting it out. So we're starting the years at 0. So subtract 1960, and we're dividing by 40 to put everything on like a smaller scale. So I think that this is a useful thing to point out, just because it's the sort of thing that maybe like from a theory perspective doesn't matter, because that matrix should have been invertible, dang it. But in real life, it's not, because it ends up ill-conditioned because of this factor. The other bit of housekeeping that I want to mention is that there's a couple of different sources of information that you all have for things related to 181. So there's the lectures that I give, there's the lectures that David gives. We have our handwritten notes during lecture that we post. We post the lecture recaps. We also have CS-181 textbook, and then there's other resources out there. Obviously, we're trying our best to make things not confusing for you. That's not the goal here. But there are going to be some small variations in how the notation is across stuff within the class. And certainly when you hit the real world, there's going to be changes or differences in notation across, how does SciPy do stuff? How does sklearn do stuff? How does, various packages on R or, something that you download off of GitHub do stuff? And so one thing we really want you to think about in the class is that when you see differences in notation, treat that as an opportunity to test your conceptual understanding of the material. And think to your goal should be like, maybe now you're at the state where someone puts up some notation and you're like, what is that? And as you go through the class, maybe your goal is to be able to come up with a guess and be like, oh, is that W meant to be a row vector? Because that would make sense in the context of the problem. Or is that beta meant to be the same thing as W, way back at the beginning of class or something like that? Again, we're going to try very hard not to confuse you. Like, our goal is not to confuse you. But when you see differences of notation, because you will encounter this out there when you go out into the real world, think of this as an opportunity and ask the questions, right? Because we definitely do not want you to be confused as you are going through class. Cool. Great. So I'm going to now share my screen and we will get started with the notes for today. All right. So that was the housekeeping. And then let's just start out with a really brief review of where we were before. So where have we been for the first 2 lectures in class? We've been in this place roughly over here. And this place is non-probabilistic, continuous Y regression problems, doing supervised learning. We have some X's and we're trying to predict the Y's that come out. And last time, what we specifically did was that we said that we're trying to predict Y. That's going to be our Y hat. And we're going to assume that we are going to use a model of this form. So there's some weights W, and they're going to be multiplied by a vector of features. So this is X. And at the very end of last class, David talked about how this X could be some phi of X, or it could be a transformation of the data that you already have. But one way or another, you have some features. And for now, I'm just going to call them X. Multiply by the weights. It's a linear combination, gets you the output. And in this particular form of notation, the bias term is being incorporated into the X. And so we had this. And so this was our model. The next thing we did is we defined a loss. So we said the loss given the data set with respect to this vector W is going to be equal to 1/2 sum over all our data points, the Y in the training set, the Y hat that we predict squared. So we're going to be looking at squared loss. So this was our loss. And it turned out, beautifully enough, that if we have this linear model and we have this squared loss, that the solution, the optimal solution for this W vector of weights is quite nice. So W star, the best vector, is going to be, and now I'm going to try to make sure that I get my transposes in the right order, because we switched some of our notation. Okay, so we get something that looks like this. By the way, any questions, like I've mentioned before, negative signs and transpose is totally the bane of my teaching. So if something looks funny, just ask and we'll reason it through. So we got an expression that looks like this. And in problem 3 of your problem set, one thing that you're doing is you're squinting at this thing. And as you even look at this, this kind of looks like a covariance, like a variance of X sort of term. And this thing kind of looks like a covariance. It's looking at the relationship between X and Y and this relationship between X and X. So kind of intuitively, maybe this kind of makes sense. If there is no relationship between X and Y, right? If these two terms here are independent, then maybe the weight should be 0, right? Because there's no relationship between X and Y. But if there is correlation between X and Y, the W's potentially should be non-zero, right? So if you kind of squint at this, it kind of makes sense. And that's something that you're making more formal in your problem 3 of your problem set due on Thursday. So that's where we ended last time. So what I want to do this time is actually 2 things. So the first thing I want to do is provide a geometric view of this linear regression problem. And this view, it still fits into the non-probabilistic bin. So we're still in this bin up here. But it's just another way to view the problem. And I think having these multiple views is important, because when you are thinking about a problem, you're thinking about why it works, why it doesn't work. Having different ways to think about it, like, oh, it's because the loss is a squared loss, or, oh, it's because this vector is a projection. Having multiple ways to key into the same concept gives you a kind of wisdom for like how to use these tools in future, right? So today we're basically going to get 3 views on the same question. The first view, you already have, that's the squared loss. We're just going to say squared loss, the thing we want to optimize. And now we're going to get 2 more views. And so the first view is this geometric view of linear regression. And in this particular view, we're going to say that we have this vector y, and this is a n-dimensional vector. And it's equal to weights transpose. And now I have to, I think, transpose this guy. So we have dimensions matching up with weights. And when we multiply these together, so this is going to be d-dimensional, right? And this is going to end up being something that's d by n dimensional, right? So if I look at this, one way that I can look at this, just from a purely linear algebra perspective, is that I have d, this is going to be kind of weird. I'm going to say it from the beginning. This is a little weird. But I have d vectors of length n on this side, right? I have d vectors in this X matrix over here that are of length n. And I am combining those d vectors, because that's what this W is doing. This W is combining the d vectors to try to produce this vector, this n-dimensional, single n-dimensional vector y. So if I draw this in pictures, again, this is a really funky way of thinking about it, but I think it's good to try to explore funky ways of thinking about things. And then if you don't like it, you don't need to use it, right? You have 2 other views on the same problem. So imagine that we have, we're in 3-dimensional space over here. And we have 2 data points. So these are our 2 vectors, x, x1 and x2, or sorry, 2 dimensions that are covered by these vectors. So these are now the dimensions. So these are the first dimensions, and these are all the second dimensions. Again, this is kind of weird because this matrix up here is d by n. Let me just draw a picture of it. We have it kind of in mind. So there's a d by n matrix. And usually, last class, we would have thought about this matrix being filled in this way, right? This is like x1, x2, x3, x4. But in this picture, we're going to actually fill it in, or think of it this way, right? There's a vector of all the first elements, a vector of all the second elements, a vector of all the third elements. And once you have this, let's say these are all the first elements. These are all the second elements. What I'm trying to produce, okay, so good point. So this is what I want, is I want to find an approximation. So I want to find an approximation to the n-dimensional y vector I have. Thanks for the clarification with these guys. So let's say my y vector looks kind of like this. So this is y. Well, the best I can do to try to explain this y with these guys here is a projection, right? So I need to think about, okay, there's a subspace that these x's create. So there's a plane that these x's have created. And I want to project my y onto that plane. And this is the thing that I can get. So now that we have the geometry, the kind of the mechanics of doing the projection is relatively straightforward. To compute the projection, we have to, for a particular dimension, we're going to end up with a sum over each dimension, x, and I'm going to use little d to mean the n-dimensional vector that is all elements of the dth dimension times the inner product of x, d, and y, and a normalization, right? So this part and this part is just creating a unit vector in the direction of xd. So you take this, and if you apply this, again, you work through your linear algebra, what you'll find, your solution will be x transpose x inverse, x transpose x y. I think I've got all my transposes properly flipped for our notation. So this was our weight vector. And this is our x. Right. So we got the same solution by saying that we're in this flipped space where the x's, our data define the subspace, and we're trying to put our x's together to create this y, which kind of makes sense, right? We're weighing our x's together to create this y. That was our whole goal. But now we can see it in form of projections. So this is one viewpoint, right? And I'm gonna leave it at that. Like, either hopefully this was like light bulb, this is linear algebra, how cool, this is amazing, or like, oh my gosh, this is confusing. If you're in that second category, that's okay. We are going to move on to another way of explaining the data. And again, the goal is to have multiple ways. Hopefully some of them stick better than others, and just having that menu is useful when you're thinking about problems in the future. All right, so now we get to our main approach for today. So now we're going to be moving into, actually, let's go to the top. So now we're going to be moving into this category over here. So we talked about some non-probabilistic methods, and now we're going to go into some probabilistic methods. All right, so for the probabilistic methods, we're going to start with a really important idea. And that's the idea, kind of key idea, is this idea of a generative model. And a generative model you can think about as a story for how the data came to be. I love generative models. Like, generative models are one of my favorite things because they give you this this story which you can interrogate, which you can understand and piece apart. You know, I mean, calculus is great, linear algebra is great, but the probabilistic view is definitely, well, I'm biased, but it's my favorite. So what's going to be the story here? So the story, in this case for generative model, is going to be that first, we have some input xn, right? Some xn comes along. What happens to that xn to produce the output? Well, we multiply xn vector by our weights. So we end up with some w transpose xn out here. And then our output is the product plus noise. And the noise, I'm going to call it epsilon, is going to be sampled, in this case, from some Gaussian distribution. All right, so what my story says is that an input x comes in, it gets multiplied by some weights, and that my y is now equal to w transpose xn, yn, plus epsilon. Let me write down epsilon n, because everyone gets a separate n. Every data point gets a separate n. So this is not necessarily real life or anything like this, but this is the story that we are going to use now to try to do some inference. And we could try to do inference on the w's, the weights, but we could also be trying to do some inference on what these epsilons are, what the sigmas are, right? So this is the story. It falls into the probabilistic category because now we're saying that we have a process by which y was created, right? We have this, what is called a generative process here from the generative model. And it involves sampling these epsilons, right? So a really important distinction, also relevant to your problem 3 in your homework, is that when we did the least squares regression, we did not assume a process, right? We just said, who knows how these x's and y's came about? We're just trying to find a linear fit in this particular case that minimizes the least squares loss. In this case, I'm actually doing something a lot stronger. I'm saying I have a story for how the data came to be. And now I want to, how can I make the story the most correct as possible, right? That's what we're going to be doing for the remaining part of this class. So by the way, I forgot. So for this geometric view, if you want more inside the textbook, you can look at section 2.6.3. And for this probabilistic view, is in the textbook in section 2.6.2. So before we go go into the next part of class, we're going to basically go into, now that we have the story, how can we solve for particular how can we use the story to solve for particular parameters? I think this is actually a really good break point for a 2-minute break for anyone who would like to just take a short break. And we will reconvene in 2 minutes to continue with this.
Sorry, could you just scroll back up to the projection formula? I didn't get to, like, the dimension you wrote. Was it for the transpose of the matrices or for the, like, let's say you wrote d-dimensional? So W is d by 1, right?
Yes. So yeah, so W would have to be d by 1. So when it gets transposed, it becomes 1 by d.
Professor, so I was also asking, I know it says W transpose X of transpose. Shouldn't it just be X?
So this is the note. It depends on which choice we use. So if we say that X, so I believe last class we were saying that X is n by d.
Yeah, I think we were stacking like X1, X2 on top of each other vertically.
So I think it's Y transpose, right? Because if W transpose is 1 by D and X transpose is D by N, then the vector you get is.
Sure, yes. Okay.
Yeah, that's,
put transposes everywhere.
this is the same convention, Skylar. The design matrix that I was working with was M by D. And I was writing each row as the transpose of a column vector. That might be
Yeah.
what you're remembering.
Yeah.
Yeah.
I remember the design matrix is always going to be n by d, where think about the rows as the examples.
So there's a bit of gymnastics involved because when we're doing the individual vectors, we had them go in columns, but the design matrix has it.
So design matrix is always m by d.
Yep.
We're going to try very hard to make sure we're consistent.
Okay, just wanted to make sure I wasn't messing it up.
Yeah,
And then
yeah,
also,
yeah.
Professor, so like for clarification, so for reference, I just did 22A, and we were talking about how this was like, so this was our closest estimation based on the column vectors of x, right, as a basis,
Yes,
effectively. Okay, cool.
exactly.
So then like my follow-up would be, so they taught us that like if you take the actual yn minus the projection of yn onto that like onto that like column basis, like the resultant vector should be like orthogonal to the entire basis as a whole. So like how does that vector relate to the error, or is there no relation?
So basically this part right here should correspond to the error.
Right.
Yes.
But like how? Do you just take the magnitude, or is there some fancy thing you do?
No, so the magnitude of that vector, this orthogonal component vector, would be the error overall on the whole data set.
Uh-huh.
It'll be if you take the right, yes. So if you take the L2 norm magnitude, right, like we have to define what we mean. And then if you look at each element in this orthogonal vector over here, then that will be the error on each point.
Oh, so that's the equivalent to our yn minus wtx squared thing?
That's right.
Okay, cool. Thank you so much.
Yeah, no, thanks for asking the question. That makes an important connection. Great. All right, so let us continue onward with this with this derivation. So now that we have the story, we can do something important here. We can write down the probability of the data given W and sigma squared. This quantity is also going to be called the likelihood of the model. So it's kind of just a naming thing. So it's probability of the data, likelihood of the model, right? Just in terms of terminology or convention. But in either case, what we're looking at is the probability of the data given the model. And that's going to be equal to the product over the entire data set, the probability of yn given xn, w, and sigma squared. Right, so far all I've done is assume that every point is IID, and that was part of my story. You know, that some input xn came along, we multiplied it by w, we added this epsilon, and I should have said epsilon here is IID, and we added that on, right? So my story told me that I should be able to factorize the probability in this way, right? My story didn't say that, you know, somehow there's correlation between the different x's. So that's our likelihood. Now we're going to take the log of this, which we're allowed to do because it's a monotonic transformation, and that's just going to be nice because it's going to turn this this product into a sum. Now we have the log probability of data given model, and that's equal to the sum over the data points n log probability of yn given xn w sigma squared. Oh, by the way, I'm going to try to remember to do all my underlines, but I may not always remember. Gotcha. So here we are. And then the next part that we want to do is let's start filling in some actual pieces. So recall, just as a reminder, what's the form of a Gaussian? So if we have a Gaussian variable z with some mean and some variance, one-dimensional, then that variable is going to have a PDF of the form 1 over 2 pi sigma squared x negative 1/2 sigma squared z minus mu squared, right? So this is just review, right, of what a Gaussian variable looks like. It's in your math review as well. In the section 0 notes, here's your Gaussian centered at mu, and the sigma tells you how wide it is, right? So that's just our little review. So this is like our detour. For our review, let's get back to our main derivation. So now we can plug some things in, now that we know this formula. And so we have sum over n data points, and then we're going to have a log, right? That's the, let me scroll up a little bit. There we go. The log is still sitting there. And we have a 1 over 2 pi sigma squared exponential of negative 1/2 sigma squared yn minus w transpose xn squared. So let's just take a moment to understand why this thing would look like this. So what's going on in this particular case is that we had the noise epsilon, right? So in our case, the mean of y that we predict, right, that we believe, according to our generative model, according to our story, we believe that the mean of y is going to be w transpose xn. And let's go back up. So that's our story over here, right? So we had this thing is going to be the mean, because the noise that we're adding, the epsilon, has 0 mean. So the mean of our y is going to be w transpose xn. And then the variance of our y is, well, this part doesn't have any variance, right? The w transpose xn, that's just a number. X is a fixed number. W is a fixed number. Later, in a couple of classes, we'll get to a case where we might have distributions over W, but for now we don't. So those are just vectors. They're fixed. So the only randomness is coming from epsilon, and the amount of variance in the epsilon is given by this Gaussian distribution with variance sigma squared. So when we're down here, this is the expression for a Gaussian distribution with variance sigma squared. And mean given by the mean that is our prediction for y, which is w transpose xn. So this is our expression. And now what we do, we can do wonderful things with logs to simplify and rearrange and such. So we can end up with a sum over log root pi 2 pi sigma squared. And then we're going to end up with a, let me make it just a minus. This x, when the log hits this x, the x is going to go away. And we end up with a 2 sigma squared yn minus w transpose xn squared, right? So this part has no dependence on W, right? Whereas this part over here has a dependence on W, and it looks just like our least squares loss. Right, so this is pretty cool. So we started out with a story of how these data were generated, and as we pushed through the story, we ended up in this particular place where this expression. so for the probability or the log probability of the data, has a term that looks just like the least squares loss. So now, if we maximize the probability of the data, we will get the same solution as least squares. And this, usually instead of saying maximizing the probability of the data, we use a slightly different bit of terminology. And the terminology that we use is maximizing the likelihood. So this solution is known as the maximum likelihood solution, for this generative model. So any questions there in terms of what we just did? Just pause. All right. Yes.
Look at questions in chat and also
yeah.
chat.
Yeah, I'm just curious, like why we decide to use a Gaussian to model the to model the noise. Like, have other distributions ever been used to model noise? Like, why are we deciding to use it?
This is a great question. So let me just include that as a note. So we could use. So the generative model is really, it is your choice of story. So this is a very simple choice, right? It's a linear mean plus a Gaussian noise. But we could use other, and as we go through class, actually, we will have more and more complicated generative models that we use to describe our probabilistic approaches. So we could absolutely use other noise models. So the Gaussian noise looks kind of like this, right? So if you had a point that's initially at this point, if this was supposed to be the mean, then you're likely to get some points around here. It's making that sort of assumption that you're not very unlikely to get out here. In about 15 minutes, when we break out into our concept checked, we will consider two other forms of noise. So we will consider so this is your Gaussian noise. And this is a great question because we'll be returning to this, again, toward the end of class. So here we could imagine that our noise is Laplace. And I would say that, I really think the noises are pretty small, right? And that's another assumption you could make. Another common assumption that you could make is that the noise actually has like these really heavy tails. So student T. So if this is your mean, then sometimes you might actually get values that are way out here for your y, quite far away from where you started. So there are a lot of choices here in terms of our noise models, and the big thing is that just like how when we started out in the linear least squares case, we were able to work out this really nice analytic solution. Similarly, in the linear Gaussian case, that's a corresponding case where we can get this really beautiful analytic solution. And in other cases where you have more fancy noise models, you have more fancy generative processes, you may not be able to get these kind of nice, beautiful analytic solutions. But that's okay, right? Because one thing that I think is very important for us to keep in mind is that in machine learning, there's always going to be this tension, or statistics more generally, between the correctness of a model and the tractability and the properties of the model. So a linear model, you can solve it and you will get the optimal linear solution, right? But maybe your data are not linear. And then you have to decide, do I go to something more complicated and risk maybe some non-identifiabilities or challenges in optimization, or do I stick with, something that's simpler, that I can optimize all the way? And that's a tricky question. And we'll get to some of that when we talk about model selection. Any other questions? No? Okay. So what I'd like to do is now, given this generative model, we can also find sigma squared, MLE, maximum likelihood estimate. Right. So when we were doing the least squares, we didn't really, so the big difference between our expression over here and our least squares expression was this 1/2, or I guess the 1/2 was there, but this 1 over sigma squared term, right? That wasn't there before. And that sigma squared term, if you're just trying to maximize with respect to W, doesn't matter, right? Because it's just a constant. And if we're just trying to minimize the least squares loss, then we don't care what the sigma squared is. But if we're thinking about fitting the generative model, right, we want to know the full story, then we may be interested in identifying what is sigma squared in addition to, what are the weight vectors for this, right? What is the noise in the data? I'm curious. I want to know. So this is something that we can do. Given this now probabilistic framework, there's a coherent way in which we can also now find the sigma squared that maximizes the probability of these data. So let's go ahead and do that. So what I'm going to do is I'm going to first just for practice, just to get us used to working with matrices and vectors, let's write our probability of data with vectors. And this is important, partly, because sometimes it's easier to do the math when you write out stuff with vectors, but partly it's also important when you start implementing stuff, because in terms of code, there are really efficient, compile libraries for doing matrix, vector, multiplications, GPUs. These sorts of operations are massively, massively efficient. And if you have to, whereas if you write some code that involves a sum, like a for loop over for every data point, that's going to be extremely slow. And you may have already noticed some of this. So being able to write out stuff in terms of matrices and vectors is useful just as a mode of thinking, and maybe it helps you connect to linear algebra views of the problem. But it's also very useful when it comes down to implementation, right? So it's good practice. So let's do it. So the log probability of the data is going to be given by, I'm just going to write down the expression and we'll talk through it. 2 pi squeeze it onto the line. Okay. So these are meant to turn into vectors over here. So these are going to be vectors of size, capital N, right? Size of the data set. And the covariance over here, so this is the expression for multivariate Gaussian, the PDF of multivariate Gaussian. The covariance is going to be just the identity times sigma squared. So it's going to be this matrix of sigma squared, sigma squared, sigma squared along the diagonal. And this is a inverse, sorry, just to be very clear. So when you take sigma squared inverse, that's going to give you a bunch of 1 over sigma squared, because for a diagonal matrix, when you take the inverse, that's just 1 over each term on the diagonal. So just looking at this, we can see that it's the same thing as the expression above. That this term over here, when we take the determinant, we're just going to end up with multiple copies of this sigma squared. And over here, when we take the inverse of this covariance matrix, we're going to end up with a 1 over sigma squared for every one of our data points, which is exactly how we want it. Right, so we have this expression. I'm going to go ahead and simplify a few things out with the logs and the determinants, and this is going to give us a negative n over 2 log over 2 pi sigma squared. So that is coming from the power in the determinant when we went down the diagonal, and also this root 2. So that's where we're getting this part over here. And now we have a negative 1/2 sigma squared, because we can just pull out that factor of sigma squared, y minus w transpose x transpose y minus w transpose x transpose. All of these are vectors. Right, so here we have our expression. And just like we could have taken the derivative with respect to w, or the gradient with respect to w, that was last class. Now we can take the gradient with respect to sigma squared. And note that I'm using gradient with respect to sigma squared, not sigma, because that is going to just generally simplify my life. The only way in which sigma appears is in this expression is through sigma squared. And so I'm not going to bother with any additional derivatives that of like sigma squared with respect to sigma. That's just going to make my life more complicated. At the end of the day, I'll just get an expression for the variance rather than the standard deviation, and that's totally fine. All right, so if we take the derivative with respect to sigma squared, we will get the following expression. I'm just going to, again, write it down, and then we can talk through it. Okay, so we have this expression over here. I think from the negative sign, we end up with a plus here. Yeah. Good. So this is just taking the derivative of this term over here, noting that the derivative of the log is just 1 over sigma squared. We had a 1 over sigma squared term over here. And so that's a -1 and the squared power, -2 power over here. Right. So now let's set this to 0. And then solve by multiplying through by sigma to the 4th, or 2 sigma squareds. And this will give us the expression 0 equals -n sigma squared. Oh, and let's not worry about that, and multiply by 2 times this, so we can get rid of these halves, right? We don't care about the halves because we're setting it to 0. We will get something that you will recognize in just a moment. Something familiar. There was a transpose up here. So last step, let's just move some terms around, and we get sigma squared is equal to y minus w transpose x transpose y minus w transpose x transpose over n. And let's stare at this a little bit now that we've done some, some of the grungy work getting through this derivation. So what we have here is, remember, this whole thing is a vector of length n that contains the difference between the true y and our predicted y, right? Because our predicted y is w transpose x transpose. So it's a vector of differences. And we are taking that vector and we are multiplying it, or taking the inner product. Basically, this term right here is just the inner product with itself, right? So we're just getting the magnitude of this vector. So the product that we're taking is just giving us the sum over n for each element in the vector of this error squared, right? So this is this expression over here is the same as the error squared, right? The residual squared. And then we are dividing by n to normalize that, that sum. So we are ending up with sigma squared. I should have written here, sigma squared MLE. This is like a prediction, right? This is not like the real sigma squared. So our sigma squared MLE is given by the sum of all of the errors squared averaged. And that makes sense, right? Because this is kind of the definition of the variance from the beginning, from our story. So if we believed that the data were shifted by a certain amount every single time with variance sigma squared, that should be the corresponding formula that we get. So it's kind of nice. At least it makes me happy when things work out this way. I'll pause now to take any questions before we go into a concept exercise. Go ahead and raise your hands if you have questions. Okay, so this is our derivation of probabilistic approach, just as review for a linear regression model. So what we did a probabilistic approach to regression, and it started off with this generative model. So the first step was to set up the generative model, and then we maximized the likelihood of the model with respect to parameters of the model, right? So in this case, the parameters of our model were like, well, what weight was it that you multiplied the W by? We don't know. Let's maximize the likelihood with respect to that. What was it? What was the variance of the noise? What was the noise? So that's another parameter that we did maximum likelihood to find out what are the maximum likelihood parameters. And as came up in the question Q&A just like a few moments ago, when we're doing this sort of thing, it's you don't have to stick with this one particular model, right? So we can come up with all sorts of complicated stories. And I think one of the things that's really powerful about this sort of approach actually is that you can incorporate a lot of expert information as well. So someone can tell you that, well, the way that this particular disease, manifests is at first there's a stage where, disease affects, certain parts of the brain affect certain parts the gut, and then you end up with your symptoms. And now you can write an entire generative process that says, well, this happens, then this happens, and this happens, and you can bake it all into your model and maybe supervise different elements separately. So that's the potential power of using something like this, is that it allows you to specify, what you think the story is for the data, and then there's just one crank to turn, which is the crank of trying to figure out how to fit the parameters of the model to maximize the likelihood of the model or the probability of the data. I'll just leave one last note. So in a few lectures, we will return to this model, and we'll put priors over, for example, W. So our story might be that W comes from P of W, then everything else happens. That X is equal to, sorry, Y is equal to, right? So this was today. But we could have made W a random variable. We did not today, but that could be part of your story, and it will be part of our story in a couple lectures from now. Okay, so I'm going to stop my share now and switch over so that we can do a concept check exercise. So for this concept check, let me just drop into the chat. Here's the form. But before you all disappear into breakout rooms, I just want to go through the question together. Let me share my screen for the question. All right. So the question that we're going to be looking at today is very related to this question that was asked about different models. Can we have different noise models? And we're going to look at the three noise models that I mentioned. We're going to look at the Laplace distribution model, the Gaussian distribution, and the student T distribution. And these are all three different pictures that you should have in your head. The Laplace is kind of very peaky at the top and then goes away exponentially. That's the picture there. The Gaussian is kind of flat at the top and then exponential tails. And the student T is also flat at the top. It has really wide tails, so it allows for bigger, larger values, larger deviations are more probable under the student T. So those are our three settings. And the first question is to take these and turn them into a loss. So what we did today is we went through and we turned the assumption of Gaussian noise into a least squares loss. We showed how those two were the same, right? By taking the logs. So what I'd like you to do here, epsilon is the error. I'd like you to, well, the Gaussian hopefully is fairly straightforward. That's just squared. But for the Laplace, and especially for the Laplace and the student T, to go through and figure out what the loss would be. What's the corresponding loss? What's the expression? And then the next part that you're going to do is suppose that you have a situation, here's X, here's Y. We have just 3 data points. And what we want to do is fit a line to these data points. And one data point is kind of out here, and these other two, let's say, are kind of forming a line. Hand wave through, right? Like this drawing is not quite, is not, numerically accurate. I think if you try to actually work it out, the lines are slightly in slightly different places, but it's conceptually accurate, right? So conceptually, which is going to be the line that's closest to the 2 points? What's going to be the line that's kind of in between, and what's going to be the line that's like ends up being pushed most toward the outlier point, right? So I'm going to go ahead and we're going to break out into breakouts, and we're going to spend maybe 5 minutes discussing those in your groups, and then we'll come back and discuss. So let's try this.
can only
All
see
right.
whether the breakout room gods are in our favor.
So hopefully everyone is now being sent to rooms. All right. As people get back, we'll return to this question. So I'm just taking a look at responses here that we have. Actually, I can go ahead and share screen with you all so you can see these responses as well. So do try to fill these out. You know, it's a good exercise to try to fill them out, and you know, taking a stab at a question, because it's not graded in any way, does force one to think about, okay, if I had to commit, what would I do? Why would I commit in a particular direction or another? So cool. So we are seeing a bit of a range here in terms of answers. Many answers seem to have about the right intuition, but not all. So let's go back to the questions and take a look. By the way, showing that hopefully shows you that whatever you answered, you were not alone. Other people were, you know, thinking along the same lines perhaps that you were. So great. So over here, in terms of connecting the generative model to a particular expression, so remember what we did. We took the log of we took the log likelihood of the error, right, of the difference between the y minus w transpose x transpose. And once we took the log of that term, that with the error, we took the log of the PDF that included the error. And then we had to do a sign flip because we were maximizing likelihood rather than minimizing loss. All right, so same, like, kind of conceptually, it's exactly the same thing. But when we look at these expressions, that's basically what's going to be happening. So let's start out with the Gaussian because that's familiar. We take the log because we're going to be considering the log likelihoods. And then we flip the sign and we end up with a term that depends on epsilon squared. So that's our solution. For the Laplace, very similar sort of story happens. When we take the log, we end up with this negative lambda absolute value of the error. And then we flip the sign again to make it from between loss and minimizing loss and maximizing likelihood. So we end up with this absolute value of epsilon term over here. There's a question of why we're taking the log. We're taking the log just largely for convenience because it makes these x go away. It gave us this really nice expression. In general, like, dealing with log probabilities is much more well behaved than dealing with probabilities, because if remember we started out with that product over the whole data set. So if every term in that product probabilities are between 0 and 1 had been like 0.1, then we would have like 0.1 to the nth power order of term, and that would be very tiny. And just like we talked about at the very beginning of class, the issue that came up with Q4 on the problem set, sure, you could do everything in just regular probability space, but taking the log is a monotonic distribution. It is a monotonic change, so it's not changing where the solution lies, but it's moving it to a space where things are better behaved, right? The numbers are better behaved. And then finally, the student T, the log is still going to be sticking around, right? So when we take the log of this term, we end up with the log of this with the -1, and then we flip the sign, and we end up with the solution over here. So that's that. And then when we look over here, this is the really interesting conceptual question. So so let's think about, who is the least happy with a big error, right? So going up here, if there's a error of like 10, for example, the Gaussian turns this into a 100, right? It's a 10 squared. And then there's an exponential involved, right? or we can even stick with it here. So the Gaussian is really unhappy. The Gaussian noise is really unhappy with this point not being well described. So if I drew line number 3, like Gaussian is pretty pissed because it's like this is a huge error. I just can't deal. If you move the line up, I can deal with a bunch of small errors. So line number 1 is our Gaussian. In comparison, if we look at line number 3 is getting 2 points exactly right. Those are going to have error 0. And then the last one is going to have some amount of error. But let's imagine moving away from that line. So the line that is going between these 2 points in line 3. If we move up a little bit, we're going to be collecting 2 errors. And we're only going to be reducing 1. Again, this is conceptual. So if we move away from line 3 toward line 1, we're going to be increasing 2 errors, but only decreasing 1. And Laplace says, hey, I don't like that because I'm increasing 2 absolute value terms a bit and only decreasing the other one by a bit. Because it doesn't care how far away you are, right? Because it's just taking the magnitude, the total magnitude of the errors. And finally, the student T is in between, where it doesn't like the big errors. Here, it doesn't like the big errors. They're also squared, but you're taking the log of them. So it's saying that some large errors are okay. I won't fit this part exactly, but I'm not going to be so pulled over to this one data point that I just have to fit that data point. So again, this is all hand waved through. You can code this up for yourself if you're curious. Just try to see what the losses are for a picture like this. It comes out roughly like this. But for now, this is the conceptual understanding of like thinking about the trade-off between fitting some points exactly and not allowing a too large error. Like to what extent are these noises will penalize really large errors. So I'm going to stop there. I'll stop the share. We will also stop the recording, but I'm happy to stick around for a few minutes.